All right, welcome to this tutorial on roots, factors, and using the rational root theorem to find all of the possible roots and then testing those roots to make sure that they are actually roots of the polynomial. So from this, we had the remainder theorem. When a polynomial f of x is divided by a linear binomial, x minus a, the remainder is equal to the value of the polynomial evaluated at x equals a, or f of a. The factor theorem stated that given a polynomial f of x, x minus a is a factor of f of x if and only if f of a returns 0. So what it means is we can use synthetic division to quickly determine if a value is a root or 0 for a given polynomial. So the factor theorem ties together this relationship between the roots of a polynomial function and its factors. However, we need a process in order to determine if roots and factors, if the roots and factors are unknown, so that we can pull these out and test them to see what they are. And so the rational root theorem states, if this is anything to write in your notes, make sure you write down this rational root theorem. A polynomial with integer coefficients has possible roots at p over q, where p is a factor of the constant term of the polynomial and q is a factor of the leading coefficient. So the process is going to look as this. We're in step one, we're going to identify the constant term, which is always going to be the last term, okay, um, without the variable. So it should just be the constant value, and record its factors, including both positive and negative values. These are going to represent the p in p over q. Step two, we identify the leading coefficient and record its factors, including both positive and negative values. These values represent the q. And then finally, the true step that we're looking for is step three, record all possible combinations of p over q. We do not need duplicates. These are the possible rational roots. So you can refer to the notes that I uploaded in Schoology to look at one of the examples. I'm going to work through an example that I'm going to pull directly from Delta Math, where all we're going to do is we're going to write down the equation, and then we're going to go find the factors of the constant, the factors of the leading coefficient term, and then finding all of the possible rational roots, and then how we use those possible rational roots in order to test for the actual roots, because there is a process in which we want to do that. So okay, so we're going to look at this example of applying synthetic division after we test for all possible, or after we determine all of the possible roots for this function, 12x cubed minus 20x squared plus x plus 3. So this is a cubic function, so it has a degree of 3. Okay, so that is the maximum number of possible roots that we are going to find, or max number of actual roots, not possible. Okay. So the possible roots are going to be determined based on the coefficient of the constant term. So in this case here, we're going to be looking at 3. We need to find all the factors of 3, which is going to be plus and minus 1 and 3. Then we're going to find all of the possible factors of the leading coefficient term, which is 12. So we're looking for all the possible factors of 12, which is going to be plus minus 1, 2, 3, 4, and 6, and 12. Okay, so the possible roots are going to be all the positive, negative as well. We're going to take p over q, so it'll be 1 over 1, 1 over 2, 1 over 3, 4, 6, and 12. And then we're going to take 3 over 1, 3 over 2, 3 over 3, which is 1, we're good. 3 over 4, 3 over 6, which is 1/2, and then 3 over 12, which is 1/4. So we are actually good here. This is all of the possible roots that we're going to have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2 possible roots. So we have 18 possible roots. We only need 3 of them. So once we find 3, we don't have to keep testing. So we're going to use synthetic division to test this polynomial to find its actual roots. So we'll have 12, negative 20, 1, and 3. Okay, and then we're going to take the first of the possible roots and test it. Okay, just keep in mind in synthetic division, the first term drops through. And now we begin testing. 112, 1 times 12 is 12. Negative 20 plus 12 is negative 8. 1 times negative 8 is negative 8. Negative 8 times or plus 1 is negative 7. That's negative 7. This is 4. So if you get a remainder other than 0, it is a non-root. So positive 1 is a non-root. So now let's test negative 1. So negative 1, we get negative 12. That's negative 32. That's 32. That's 33. It's negative 33 and 30, negative 30. So you can see that positive and negative 1 are not roots. So let's try another. Let's check the next one here. We're going to do 1/2. Half of 12 is 6. Negative 20 and negative 6 is negative 14. Half of negative 14 is negative 7. Negative 1 and negative 7 is going to be negative 6. Half of negative 6 is negative 3. And 3 and negative 3 makes 0. So we have a root at 1/2. Okay, we'll test another one. Let's go with negative 1/2. Okay, so that'll be negative 6. That's be negative 26. That's going to be 13. That's 14. That's negative 7. And that's going to be negative 4. So negative 1/2 is not an actual root. Okay, let's check 1/3. 1/3 of 12 is 4. Negative 20 and 4 is negative 16. That's going to be negative 16 thirds. And let's see, 3/3 negative, so be negative 13 thirds. And threes are going to cancel. This is going to leave us with negative 13. And then we'll have negative 10. So 1/3 is not a root. Let's test negative 1/3. Okay, so it'll be negative 4, negative 24, 8. That'll be 9. Negative 1/3 of 9 is negative 3 and 0. So it looks like we have another root at negative 1/3. So we just need one more. Let's test 1/4. Okay, 1/4 of 12 is 3. That'll be negative 17. That'll be negative 17 over 4. And that will be this 4 over 4. So it'll be negative 13 fourths, which would be negative 13 and negative 10 again. So negative, or no, positive 1/4 is not one of the roots. Let's go negative 1/4. We have negative 3, so negative 23. That's 23 fourths. And that's going to be 27 fourths. And then that's going to be negative 27, which is negative 24. So positive negative 1/4 is not one of them. I'm going to move on from the fractions because I have a feeling that it's probably going to be the 3, so I just want to check it before I have to keep testing on these fractions. Okay, so we're going to go 3, 12 makes 36, and 36 negative 20 makes 16, 3 and 16 makes 48, that makes 49, and you can see that that positive 3 is not going to be one of them either. Let's try negative 3. Negative 3 and 12. That's going to be negative 36, be negative 56. That'll be It's not going to be 3. You can see it's just going to keep getting bigger and bigger. So positive negative 3 is not one of them. Okay. Let's try 3 halves. 3 halves of 12. So that's 6b. Half of 12 is 6 times 3 is 18. That's negative 2. And then that's going to be negative 3. That's going to be negative 2. And that's going to be negative 3. There we go. So the other root that we were going to have is going to be positive 3 halves. Okay. We could then take these roots and write our factors in them. If we were to write the factors, we would initially start off as x minus 1/2. Remember, do the opposite. The other one would be x plus 1/3. And then x minus 3 halves. Now, our factors need to have integers only, no fractions. So for this first one, I'm going to multiply it by 2, so it becomes 2x minus 1. The second one's multiply it by 3, so it becomes 3x plus 1. And the last one will be multiplied by 2, so it becomes 2x minus 3. So this would be the factored form of the polynomial from above.